Hello, so continuing on this Leetcode contest 162, the third problem was 1254, number of closed islands, and the problem says we get a grid that has zeros and ones. 0 represents land and 1 represents water, and we consider an island to be a maximal 4-directionally connected group of zeros. That's basically what a definition of an island here. It's when you have connected group of zeros that in all four directions it has ones as borders basically, and we want to return the number of closed islands. So you can see in this example here we have this number of zeros here that have the blue ones as border on all four directions, and the same thing for this single zero over here. And so as a result we return 2, right? If we look at the second example, we have only 1 0 here that has border of 1, the rest don't have a border of 1, and so we return just 1. And if you draw this one, you realize it has 2. These are the constraint, and the grid has only 0 and 1 values, so we don't need to worry about anything else. And yeah, so let's see how we can solve this problem. So this is very similar to like counting the number of connected components when there are zeros, but here it's a little bit different, where we are using, there is the one thing that is different here, where usually in these kind of problems land is represented by 1 and water by 0. Here is the reverse. That's fine, we could just change the checks that we will do, but with the connected components with the zeros, we could solve it with DFS. And so the first thing to come to mind here is let's just adapt DFS to work with this case, and that's what I will do in the overview here for this solution. Okay, so let's see how we can solve this problem. So I just draw here an example so that you could see how we can solve something like this. So the idea here of this solution is to do 2 passes basically, but still with the original idea of using DFS. So 2 passes of DFS. So what we would do in the first pass is, our problem mainly is these here, this case here, where we have the border here is not 1. So the problem comes when border of a set of zeros of 0 is not 1, like any border, right? So that's our main problem. So what we can do is just focus on this, and those cases where the border is not 1, which are this one and then this one. So in the first pass, what we will do is basically replace these with 1s, because these don't count. We shouldn't count these as closed islands, right? So just replace them with 1s using DFS. So basically what will happen here is that first pass of DFS, fluid fill, we just fluid fill this, basically replacing with 1s all the connected zeros that have an edge that is a border and it is 0, right? So fluid fill all connected component of zeros that have a 0 as a border, right? And once we do that, basically we are done. After that, and then in the second step, just count the number of connected components of zeros, right? And using DFS also we can do this. The second step is the usual problem that we have. We get something like this. We have zeros as that are like have 1s next to them, and we want to count the number of connected zeros, or the number of components that are constituted of zeros. So this is the original, so this is the idea of what we will try to do. So basically once it becomes like this and these values became 1, then after that is pretty straightforward to detect the components. So this one ends like this, and you can see it has all ones next to it, and then the other one is this one, and so right away we will return 2 as the result, right? So that's pretty much all there is to it. Now coding it maybe will be actually pretty straightforward, I think, just using the usual DFS. So let's code this idea up and see if it passes test cases. Okay, so let's start coding this solution. So we said that there are 2 steps. The first step is remove all zeros, connected zeros that have a zero as a border, right? And then after that, just count the number of connected zeros or connected components of zeros. So that's pretty much it, and we will be relying on doing our DFS, right? And DFS will usually start from at some point, and then we will need to go through the first pass, which is here. We need to go through all, find basically these places that have zeros as borders, and so that would mean going through. Let's initialize. I usually like this to be named M, so let's name it M, and then we'd have N and M as the length of the grid, and the length of the grid 0. Or actually, now that I named it M, I should just do this. And this is N, and this is in range of M. And now we need to look for this case here. And that case is, first the value has to be 0, right? And after that we check if it's a border. So and is in border, right? So let's pass that ij and let's define that function. Or actually on border. And so let's do that. So what does it mean for it to be on a border? So basically, if the I is either equal to 0 or I is equal either in the left border, like the top border, so I is 0, so either top border or the bottom border, right? So that's n-1, or j is the left border or j is the right border, right? And we need only one of them to be true, so that it's either the top one, the bottom one, regardless of j, or the left one or the right one, regardless of I, right? So that's the first step. So what we do, if it is a border, we want to float fill and replace its value and all the values connected to it that are zeros. We want to make these to be ones. So what we'll do here is we will DFS on that value, and here DFS just float fills and replaces all connected zeros to ij with 1, essentially, right? So we will have x and y. I'll just define a function that returns the neighbors of I and j, and we will just DFS on the neighbor, right? That's what float fill does. And what this function does is replaces with 1. So that's what we want to do. So j equal to 1. And here we want to just make sure that we are not calling it in something that is out of bounds, right? And so for that to be out of bounds, it just needs to be like, so basically let's just is out of bounds. Let's also define a function for that, just to make this more readable. Or if it's already visited, right? And it's already visited, we already mark that here with 1. So no need to add something else, that like a visited set, to keep track of that. We are already changing the values. If it's 0, we are already changing it. So different than 0, then we want to stop, right? And also if If the value is 1, which means we no longer have connected 0 in this direction, so we should stop also, right? And let's just write this one. So for I and j, and this happens basically when it's not in bounds, right? Which means it's basically not between in the bounds I, n, or if j is not in the bounds, right? Maybe out of bounds, like this. And then after that we will need to so now we did our DFS. So we called it here. So now we did the first step. Now the second step is just to count them, right? So we count the closed islands, right? So closed islands. That's what we call the problem called them. Yes. Okay. So let's just do the same traversing here, so that we can count all the connected zeros, right? And so same thing here. We check if the value is 0, because if it's not 0, it's definitely not a start of a component that constitute a closed island, right? And if it's equal to 0, we do the DFS. And since we removed the connected components that are zeros that are not closed island, because we replaced them with ones in this step, that means we can just count any connected components now, because we are sure now that it has borders 1, because all those that didn't have borders 1, we replaced them with ones, right? And so here we could just right away just count immediately, like we are doing normal DFS, counting the number of connected components. And after that we can just return that. Here I need to, there's one thing that I didn't define, which is calculating the neighbors of position. And so the neighbors are just for so it's just pretty much for ni and j in, so it's basically going left, right, top, and bottom, right? So it's I plus 1 j, I minus 1 j, I j plus 1, and I j minus 1, right? And we want to read, Python has this handy thing called yield, which will just basically return to a for loop every time a new value is returned by this. So we could just do that like this. We could also just copy this this here and put it here. It's just more readable to have neighbors here. And that's pretty much it. So let's run this. Index out of range. So usually if it's so this is in range, right? And we are saying not. And if it's not, we wanna actually it's end. So it's in range if these two are true, and it's out range if the reverse, so not of that, right? Okay, cool. Let's submit. Okay, so that solution passes. So one thing you could think of is, okay, so it's cool to this is a cool solution, but it uses 2 DFS paths. Can we get this down to 1 path, right? And that's certainly possible. So let's see how we can change this solution here to do that. And so we'll just remove this path, right? We will keep the rest because that's useful utilities here. And now what we will be doing so how can we solve this solution differently? So let me just get rid of these changes that I made here. Oops, sorry about that. Okay, so let's leave this as zeros as it was before, right? So now the difference in this solution, since I want to do 1 pass, so instead of doing this, so this one here was solution 1, So instead of doing that, solution 2 here. So what would happen is that I would just do the second step, except with one difference. If I find any case where essentially where the border here is 0, in my DFS I would return false. So if basically what would happen is that if during DFS a connected component of zeros is found, but with border as 0, any border or any side, return false, right? Otherwise I return true. Otherwise return true, right? And that way what I can do is just count the number of true values. So I would count and so basically what this means is my DFS now, instead of finding the connected components of zeros, it will find the closest islands of zeros, right? And so basically using just a Boolean value, let's say call it res, that I will initialize to true. So I would suppose during my DFS that my island is closed, and then when I find a 0 at the border, I would say, okay, my res, add to it that I found false, right? So that basically anything else, any other neighbor that says, okay, true, I'm still closed interval, maybe because, for example, because of this 0 where it has 1, 1, and so it reports that it has 1s as neighbors, and this 0 reports it has 1s as neighbor, but this one will say, I'm a border, and so false, and so ending it with false would mark the entire DFS of the component as to return false. And since the entire check for that connected component is false, I won't count it. And that way I will be excluding all these connected components that have 0 as a border, just because I'm doing an AND where anytime a border, any points that is connected only to zeros and then their border is 1, returns true. But if any one of them finds one next to it that has a border, it will propagate false, and I will end up returning false, and I will end up not counting that element. The other change is that to mark the visited set, I will be using value 2, since value 2 is not in the array, right? Because I won't be marking these as 1s. So I would need to be careful there and just put the value 2 to mark visited. And that's pretty much it, I think, for this solution. The rest is just normal DFS that we will that we did in the previous solution. Okay, so let's code this up and see how it works, and see if it passes the test cases. Okay, so now let's code that solution, the second solution that we just saw, and see if it passes the test cases. So I left these method that we will be using for this second solution that won't change really. So what we said is that we will just check if anytime we find a 0, we will start checking if that connected component of zeros is a closed island. And so to do that, I will just call DFS on INJ, but first I will mark that position as visited. And as I said, I'm going to use the value 2 to mark a position, a cell as visited. So I would just say that IJ is equal to 2. And if this returns a true, so basically my DFS will return true if the connected component of zeros is a closed island, right? Otherwise it would return false. And so basically now I know that it's a closed island. I could just say, okay, let's take my closed island here and add 1 to them, and I return that at the end. So now let's make my DFS return false. So as I said, I will use a Boolean that initializes to true, so I suppose it's a closed island first, and then I check the neighbors and see if any of them finds a 0 at the border, because any 0 at the border means I don't have a closed island, right? And so what does it mean to find the 0 at the border? If I reach a position that is out of bounds and I haven't reached a 1 position yet, that means that I had a position at 0, because 1 will block me from going to a neighbor, right? And so first let me just do an I and j in neighbors. So I'll just use the neighbors that I had earlier. Now if is out of bounds, so if this neighbor is out of bounds, what does that mean? Let's hold on that for a moment. And then now if the value is in bounds, because we went to the else and the value is equal to 0, that means that I'm still in a connected component of 0, so I need to continue. So I need to do DFS on that next position, right? But I will need to mark it as visited, and marking as visited is just doing an I and j equal to 2, right? Now I said that I need to end the result for each neighbor, because if this one returned me false, saying that I found the 0 at the border, I should end it with this, so that this overall can be false, and so that I don't count it, right? So at the end, my DFS will return that result, right? And this basically means is closed. Now, if it's out of bounds, if we reach it out of bounds, right? What does that mean? That means we went here and we found that it's equal to 0 at the borders, right? But we called the neighbor. So the value was 0, and then we went to the DFS and called the neighbor until we got out of bounds. That means that we didn't find the 0 that stopped us, right? So that means that we found the 0 at the border. And so that's the case where our is closed should be set to false, right? And that's pretty much all there is to it. So this case here means that we found a 0 at a position border, and then we continued to its neighbor, and then we found an out of bounds. And at that point, it's not closed. I hope this explanation makes it a little bit clear. And so that's pretty much it. Now we can just run this. It's pretty much done, right? We have the other methods already, and that's pretty much it. So I didn't use that this is in border in this case. I could have just checked it is in border also in this, instead of checking out of bounds on the next iteration. Yeah, you could try that if you want. So let's just run this and submit. So this solution also passes. In terms of time complexity, you can see here we are doing O(n) by m, right? And then in the DFS we go through at most the entire grid, because maybe it's entirely it's like all the grid has zeros and just the border is ones, and so at most it would be this basically squared, because we are doing a DFS here in the internally. So that's the overall time complexity here. Yeah, I think. Yeah. Okay, so thanks for watching, and see you next time.